Okay, so we were talking yesterday about Pauli matrices and the way that they generalize for arbitrary spin. I just reached this point. It's interesting to understand the connection between Pauli matrices and the slightly strange things that happen with spin a half. And then it's also good to study the case spin 1, and there's a set problem on that, which I recommend to you. And then moving right along to the case of very large spins, so that we hope to recover classical mechanics and understand how bodies which have macroscopic, have many, many h bars worth of angular momentum, end up pointing in some very well-defined direction. The procedure for generating the Pauli matrices is completely general. We're just writing down a matrix, each entry of which is the value of whatever operator, here Sz, squeezed between states of well-defined orientation between the states. So this is the matrix made up of S, M primed, Sz, Sm. And it's very straightforward to work out what these numbers are. They're perfectly trivial in the case of Sz, because these are states of well-defined, this is an eigenstate of that operator with eigenvalue m, etc. So we just have down the diagonal the possible allowed values of m, which range from s to minus s. So this is the bottom of that matrix. And in the case of Sx, we replace Sx with a half of S plus S minus, and then we have nothing down the diagonal, but we have non-zero entries just on the diagonal that lies one above the main diagonal and on one below, and zero everywhere else. So that's just a generalization of the Pauli matrix, in which only this part, in the case of the Pauli matrix, only this part exists, where this is a function alpha of, this S minus 1 is playing the role of m. So alpha of m, sorry, this should be an m, and this should be an m, is what you get. Sorry, this is with the raising operator, so this should be m plus 1, right? Sorry, it's this object here, just some square root. So, for example, it's very straightforward to pick a large value of s in the this diagram here, which should be up there, is for the case of s equals 40. And then for this large value of s, to have your computer find the eigenvalues, sorry, not the eigenvalues, we know the eigenvalues. Out of these three matrices I can construct, if I take n is equal to, for example, nothing sine theta comma cos theta, so this is a unit vector which lies in the this is theta, this is the Ez direction, this is the Ey direction, so this is the unit vector n. So if I take any unit vector whatsoever, it has some coordinates like this, then I get the matrix for spin down that direction being nx sx plus ny sy plus nz sz. So choose some angle theta. Take the appropriate linear combination of Sz and Sy. I haven't written down Sy, but it's essentially the same as that with a 1 over 2i and some minus signs. And then have your computer solve this problem, that Sn on a vector, which will be a 40-component vector, A1, A2, down to A40, well, AS in general, is equal to, let us say, S, A1 through AS. Then what are you doing? You're finding the state in which you are guaranteed to get the value S, in other words, the maximum possible value for the angular momentum in the direction of n. And you're expressing that state as a linear combination of states with different amounts of angular momentum down the z-axis. So these numbers are the relevant linear combinations there. So what we're saying is that that n, s in the direction of n is going to be a1 of s in the direction of z plus a2 of s in the direction of, of s minus 1 in the direction of z plus, and so on. And actually, this isn't of length s, it's of length 2s plus 1. Because there are 2s plus 1 possible orientations. So if s is 40, this is going to be 81, an 81 component vector. So have it do that, and what you find is what's shown in this picture up in this diagram here. This is for three different values of cos theta. So this is for cos theta is 0.5. This is for cos theta, sorry, minus 0.5. This is some other value of cos theta. Can't quite read it, and so on, right? So for this, if you take this value of cos theta, which I suppose is minus 60 degrees, then these a's, which of course are complex numbers, have moduli that look like this. So they're non-zero in some interval around here, which is to say, so what does that mean physically? What are these numbers? This is the amplitude that if you would measure along the z-axis. So first get your system into this state. Your system being in that state, we would understand it to say that its spin is in the direction of theta. What then is this becomes the probability to measure that it has s units of angular momentum along the z-axis. This becomes the amplitude to find that you have s minus 1 units along the z-axis, and so on. So if the angular momentum, if the angular momentum vector really were at direction theta, how much would we expect to find along the z-axis? So classically, in this state, theta n, we expect Sz to return S cos theta. S cos theta is the projection of a vector of length s pointing in the direction of theta. It's the projection of that down the x-axis, down the z-axis, sorry. So, and what you're finding here is that these amplitudes peak around the place where classical physics would say this is the answer, and the quantum physics is saying, well, you have a chance to get all these answers with probabilities which are given by the square of these numbers, so quite strongly peaked. And as you change theta, so as you change the vector, you change the state, the input state, you change the direction of your spin, you change the place where these amplitudes peak. So that's only for s equals 40, and classical objects have s of 10 to the 30 or whatever. And as you get more and more, as s becomes bigger, there are more and more of these dots along this line here. There are here 81 dots, I suppose. 81 numbers are being calculated, right? Because there are 81 components in the vector. By the time you've got to 10 to the 31 dots, you'll find that that they're really completely peaked around here. So that's how we, out of this quantum mechanical stuff, we recover at high spin the classical idea that things point in some definite direction. And you can go on to show that the expectation value of Sy, which classically should be S sine theta, is indeed S sine theta. And what's more, the uncertainty, you can work out the RMS, you can work out what the expectation value of Sy squared is, and you find that that's essentially the same as the expectation value of Sy itself squared. In other words, there's very little uncertainty at high S in what you will get for Sy. So what's happening here is, in quantum mechanics, we have to calculate a whole series of numbers, which are the components to describe. So to describe the spin state of something, we have to construct, in the case of spin 1/2, 2 numbers, in the case of spin 1, 3 numbers, and so on. 2s plus 1 numbers we have to calculate, being the amplitude to find the various possible answers on Sz if you would make the measurement Sz. what we're doing essentially is recovering the probability distribution for the SZ measurements, which in classical physics is a delta function glitch at s cos theta. But in quantum mechanics, our probability distributions are not delta functions. They're some kind of spread out things, and you're seeing what they are there. But as you go to higher and higher spin amounts, the probability distributions narrow down around the direction of spin, which classically, so in classical physics, we say the direction of this spin is given by the Euler angles, or by the polar angles theta and phi. We just have some completely definite, oh, come on, you stupid thing. We have some completely definite direction, and whereas in quantum mechanics we need a whole load of numbers because we're defining a probability distribution. In classical physics, it is strictly speaking a probability distribution, but it is a delta function, and all we have to do is specify the center point of the delta function probability distribution, and we do that with just two angles. And in quantum mechanics, we need a load of different numbers to spell out the whole probability distribution properly. Now, the other thing I wanted to say on this topic of relating quantum mechanical levels of angular momentum to classical levels of angular momentum is the importance of this. So we know that S squared has, the total angular momentum operator has E values S plus 1, which is clearly greater than S squared. And remember, this thing came into the world as the maximum value of the angular momentum around the given axis. So, and how much greater this is than this depends on the value of S. So, when S is a half, we have that S plus 1 is clearly equal to 3/4, which is 3 times the quarter squared, a half squared. Right? This is the maximum value. And that's telling us that you always have a third of your spin down each of the three axes if you have a spin half particle. And the most you can ever know is whether the one component is pointing this way or that way. But we never remotely get the spin properly aligned with one axis because there will always be two units of angular momentum somewhere or other in the plane orthogonal to that chosen axis. So when we have S is 1, we have S plus 1 is equal to 2, which obviously is 2 times 1 squared. So now the amount of angular momentum we can have down one axis is a whole half. Here it was only a third. Now it's become a half of the total angular momentum, and each orthogonal, each direction in the perpendicular plane has less than in the direction that you've chosen to align the angular momentum with. As you go down to large values of S, you have that S plus 1 is practically equal to S squared because obviously S squared is going to be, by definition, bigger than S. And that means that we can get essentially all of our angular momentum pointing down a given axis. So the important message is from this that we're familiar with this regime where we can get something to point in a well-defined direction. But the atomic world works in this regime where there's always loads of angular momentum in the directions that you haven't been working on. Okay. So I now want to turn to a new topic, which is the addition of angular momenta. The last thing we have to do with angular momentum. So this is a very important topic for atomic physics because atoms contain, the simplest atom, hydrogen, already contains a proton that carries a half h-bar of spin. An electron has the same amount of spin, and then the electron may have orbital angular momentum. It may have angular momentum by virtue of its orbit around the proton. So generically, a hydrogen atom contains 3 units of angular momentum, and we want to know, so what are the states of the atom in which the atom has well-defined angular momentum? So we're going to study And this is an application of the machinery that we introduced, I guess, early this term to discuss composite systems. This is a classic, this is an application of our theory of composite systems. So if you feel unsure about the theory of composite systems, please go back and have another look at it, because this is what we're going to be applying. So all that stuff about Einstein, Podolsky, Rosen, etc. What underpinned that. Because what we're going to do is we're going to consider two gyros. We're going to have gyro 1 has J1, so it has total J1 plus 1. So it has M lies between minus J1 and J1. So that's the rate at which this gyro spins is fixed by some servo motor or something, right? And it's spinning at this rate. And we're going to have gyro 2, which obviously is going to have total angular momentum squared is this. So this will be M1, and M2 is going to lie between minus J2 and J2. So we've got these two gyros. There might be objects belonging to a navigation system, and we're going to stick them inside a box. And they're not going to talk to each other. They're going to have, there's going to be no Hamiltonian, there's going to be no coupling, physical coupling between these two gyros at all. But we are going to put them in a box, close the lid, and then say, so what are the states in which this box has well-defined angular momentum? And they will turn out to be, what we will find is that when the box has well-defined angular momentum, if you open the lid and ask what happens if I look at the angular momentum of gyro 1, I will get a variety of different answers. It will be uncertain what I'll find for gyro 1. And gyro 2 will have an angular momentum which will be correlated with gyro 1. So when the angular momentum of the box is well-defined, it has a definite amount of angular momentum and it's pointing definitely in some, well, the amount parallel to the z-axis is definite. When you look inside the box, you'll find it is uncertain what the angular momentum of the bits are. And we'll explain physically that it's a physical necessity that that's the case. That's not mysterious. But we'll, I hope, make it evident that that's so. Right. But the moment we're going to address this kind of mathematical problem, we know that the states of the box... no, sorry. So the states, we have two sets of complete sets of states. Complete sets of states are going to be J1, M. There's a family like that, and there's a family J2, M2. Sorry, this should have an M1, shouldn't it? Since we know what the total angular momentum of the first gyro is, the only thing to discuss is what its orientation is. And if I consider the set of states like this, J1, M1, with M1 ranging between minus J1 and J1, that's a complete set of states for the first gyro. This is a complete set of states of the second gyro. In other words, we will be able to write any state of gyro 1 as some sum A, M1, J1, M1, etc. Right? So what are the states? What's a complete set of states of the box? It's the set of states J1, M1, J2, M2. Right? We discussed that if we have a system A and a system B, a complete set of states is obtained by taking a member of the complete set of A and multiplying it by a member of any other member of the complete set of B. If you take linear combinations of those, you get everything. In other words, the box can quite generally, the state of the box can be written as some sum of B, M1, M2, J1, M1. Whoops, that's meant to be a pointy bracket, J2, M2. And we want to find the states of the box. So any state of the box can be written like this, where these numbers, for suitable choices of these numbers, these amplitudes. What we want to do is find the states of the box which are eigenfunctions of the box's angular momentum operators. And do you remember that when we discussed these things, these composite systems, we had that, that you added the operators of systems, of subsystems, and you multiplied their kets. That's how it worked. So we want to consider now what the relevant operators are. Well, we're going to have, for gyro 1, we have J1 squared, we have J1z, and we have J1 plus and J1 minus, the raising and lowering operators, where this is equal to J1x plus or minus I J1y. And of course, we will have the same kit of operators for the second gyro. That's for gyro 2. And then for the box, we will have J squared, which will be J1 vector plus J2 vector squared. And we will have Jz, which is equal to J1z plus J2z. And we will have J plus minus, which is equal to J1 plus minus plus J2 plus or minus. So we add the operators belonging to distinct systems. Here, because it's a squared, right, this thing should be the vector operator belonging to the box squared. So we add the individual, the vector operators belonging to the individual boxes. So we have to do a bit of, these are fairly straightforward. We have to do a bit of footwork on this. So let's find out, let's expand this. We have that J squared for the box is equal to J1 plus J2 dotted into J1 plus J2. And this is not, there's nothing funny going on here because the operators belonging to distinct systems, another thing we covered in the composite system discussion, operators belonging to distinct systems always commute. So we can multiply this out just as if they weren't operators, but just ordinary boring vectors, and find that this comes to J1 squared plus J2 squared plus J1 dot J2 twice over. This is because J1i, J2j commutator vanishes. Operators belonging to distinct systems always commute. Well, this is fine. This is in our list of operators. But this is not in our list of operators, right? J1.J2 is not up there. So we need to write this in terms of things that are up there. So we say J1, I want to get an expression for that in terms of the things already written up here. And what I do is I say, let's consider J1 plus times J2 minus. That is J1x plus ij1y, J2x minus ij2y, which is going to be J1x dot times J1x times J2x plus this on this will give me a J1y, J2y, which these are two of the components, the elements that are buried inside the J1.J2. But I get other stuff, unfortunately, which is I get plus I J1y, J2x minus J1x, J2y. So this I want, this I don't want. But we can get rid of this by arguing that if I write down J1 minus J2 plus, so reverse the plus and the minus, everything will carry across. The first two terms will emerge. But what will happen here is that this will become, this minus sign will migrate from here to here because I've changed where the minus sign happens here. So I'll get minus I j1y j2x plus, sorry, minus j1x j2y. So when I add these, the left sides, these pesky terms that I don't want will go away, and I will have that j1 plus j2 minus plus j1 minus j2 plus is equal to twice j1 dot j2 minus j1 z j2 z. Right? Because these two taken together make j1 dot j2 minus the z bits, right, which are inside here. So now we have what we want, which is an expression. I now go back to this j squared here and replace that with stuff to do with j plus and j minus. So I now write that j squared is equal to j1 squared plus j2 squared, j1, and then I want this, so I take this. I take plus j1z j2z plus j1 plus j2 minus plus j1 minus j2 plus. So this disgusting mess on the right expresses j squared, the total angular momentum operator of the whole box, in terms of operators whose action upon the states of the box I know. That's the key thing. What I've been doing here is getting an expression where I know what every one of these operators does on those states of the box, j1, m1, j2, m2, right? I do not know what jx or jy does to those things. It makes a disgusting mess, but I know what every one of these operators does to those things. That's the purpose of this algebra. Okay, so now a little physical argument. Suppose you've got your first gyro pointing in the z-axis, sort of aligned with the z-axis, and you've got your second gyro aligned with the z-axis. Then you'd think that your total angular momentum would be the sum of the angular momenta of the two gyros. Because they were both parallel to the z-axis, you would argue they were parallel to each other, and you'd have the total angular momentum in the z direction. So what we do now is we investigate j1, j1, j2, j2. This physical argument suggests that this is the object j1 plus j2, comma, j1 plus j2. So this is a state of the box in which it has this much angular momentum and all of it pointing down the z-axis on the grounds that if you take two gyros both pointing in the z direction, surely you've got a box surely their angular momenta just add. So we want to show that this is the case. Physically, it seems reasonable physically. Is it true? We check that it is true by applying the relevant operators to both sides, right? So if I do jz on this, I'll just say jz on the left-hand side. What do I get? I get j1z, j2z plus j2z, right? Because j total z is the sum of the z operators of the gyros operating on the right-hand side, which is j1, j2, j1, j1, j2, j2. So the way these composite system operators work is that this looks at this, and we get j1, because this is an eigenfunction of this operator with this eigenvalue, times j1, j1. This stands idly by, j2, j2. So that's that, and then I have plus. This looks at that and produces a j2, j1, j1 standing idly by, j2, j2 produced as the eigenket. So indeed, we get j1 plus j2 times what we started with, j1, j1, j2, j2. So that confirms that this object is an eigenfunction of this operator for the box with the expected eigenvalue. Yep.
In a couple of lines above j squared, is there a factor of 2 in front of j1z, j2?
Yeah, there probably is, isn't there? Because this came across onto this side, and we wanted a 2. Yes, thank you very much. There is a factor, and this was about to be important, isn't it? There is a factor of 2 there, because we wanted a 2 j1, j2 from up there, and we had twice this, which came onto this side of the equation. So that's that. Now we check j squared. What does j squared do when it's applied? Well, it's going to be j squared on this. So j squared, I want to do j squared on the right side, and j squared we've discovered is j1 squared plus j2 squared plus 2 j1z j2z plus j1 plus j2 minus plus j1 minus j2 plus. All that disgusting mess has to operate on, it operates on j1, j1, j2, j2. Well, this is an eigenket of this operator with eigenvalue j1, j1 plus 1. And it will then return this, and we'll find that this gets returned, so I'll just stick it in the back as a common factor. Similarly, this one looks at that and produces j2 plus 1 times itself. Then j1z looks at this and produces a j1 times this. And j2 looks at this and produces a j2 times this. So now we have a plus 2 j1, j2. And that's the action of this operator on this product. Then j1 plus looks at this, tries to raise this trailing j1 to j1 plus 1, but it can't because we're already at the top, so it kills it. So the j plus operating on this kills it, and it does not matter what j2 minus does to this because it's multiplied by nothing. Similarly, when this j2 plus operates on this, it kills it, trying to raise that j2 to 1 more. So the action of these two operators on this is to produce nothing, and I can close the bracket just there. So j squared, actually this really should be on the right-hand side. J squared on the right-hand side produces this bracket times this ket, which shouldn't have been written so far to the right. And we can now rearrange this because we've got two j1, j2s. I can take one of those j1, j2s and deal with it by putting it inside there. So I can write this as j1 plus j2 plus 1. So to this bracket, I've added a j1, j2. That's one of those. And the other one I put inside this bracket by writing it as j2 times j1 plus j2 plus 1. So this one, this j1 produces a j1, j2, which is the other one of those. So this is how much I've got of j1, 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 j2, j2. And now I can immediately see that this is j plus 1 of j1, 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 j2, j2, where j is j1 plus j2. So that proves that it proves the conjecture we started with, that this object is an eigenstate of the box with the eigenvalue, with the total angular momentum eigenvalue j1, j2. So this establishes, so we've proved by hard work that jj this being the state of the box, is equal to J1, J1, J2, J2, where J is J1 plus J2. That was rather hard work. The next bit's easier because we can now apply the minus operator, the J minus operator, to both sides of this equation. And on the left side, we'll get some multiple of J, J minus 1. On the right side, we'll get something more interesting. So now we apply J minus, which is equal to J1 minus plus J2 minus to both sides. J minus applied to J comma J produces, there's a square root here, which turns out to be J plus 1 minus, it should be M plus M minus 1, but M is J, so minus J minus 1 times J comma J minus 1. So I've applied the box's tipping operator, lowering operator, whatever you want to call it, that tips its angular momentum away from the z-axis, and we get this multiple. I'm appealing to the stuff we showed when we started on angular momentum for this square root, times the state tip where we're tipped 1 unit away from the z-axis. So that's what we get on the left-hand side. So this is the LHS. On the RHS, we have that J1Z plus J2, not Z, minus, take J1 minus, J2 minus. This sum is the same as this, operating on J1, J1, J2, J2, which we've proved is the same as this. What does that give me? It gives me the square root. So this J1 minus interrogates that. It produces a square root. Well, let's evaluate this square root. Sorry, this square root simplifies because we have a j squared and a j squared with a minus sign and a j with a plus sign. So this becomes the square root, in fact, of 2j, j minus 1. So what we're going to get now is the same situation. We're going to have j1 minus working on this is going to produce the square root of 2j1 operating on and the output will be J1 minus 1. This will stand idly by whilst that happens, J2. And then we have to add, that's this plus sign here, the result of J2 minus banging away at that whilst this stands idly by. We'll get a root 2J2, J1 standing idly by, J2 minus 1 being produced. So we have that. We can now equate the left and the right sides again. We can say that the state J, comma J minus 1 is the square root of J1 over J of this Johnny, J1, J1 minus 1, J2 plus another square root, which is J2 over J of J1, J2 minus 1. So what have we shown? We've shown that when the box has angular momentum that's tipped a touch away from the z-axis, if you open the box, there are two, and look at the individual gyros inside the box, there are two outcomes you might find. You might find that the first gyro is tipped away from the axis and the second is still parallel to the axis. Or you might find that the first gyro is on the axis and the second is tipped away from the axis. And it's inevitable that has to be the result. One of these gyros has to be off the axis, but they can't both be off the axis, because then we'd be 2 units of angular momentum down the axis short. So what we've got here is correlated states of gyros. The gyros have become entangled. In this state in which the box has well-defined angular momentum, the results of measurements of the 2 individual of the gyros in the box have become entangled. Let's make a picture now to help organize these calculations, because we've just begun, unfortunately, on what in principle is an extensive exercise of calculating, but from now on it's almost mechanical. The way to go is to put your original state, J, up here. Why am I putting it up there? Because the origin is somewhere like here, and this is J units up from the origin, and this is J units down, right? So here we have a minus J. It's J units down. Here's the origin. We started with this state and established what it was, that it was J1, J1 times J2, J2. Then we used the lowering operator, J minus, to move around this semicircle to a state here that we've just constructed, which is J minus 1, which turns out to be a linear combination of this and this. And we found out what the factors are that make the linear combination. And we can now take this state, and we can apply our lowering operator on this to generate a state here, which will be J minus 2. And let's imagine doing that. We won't do that, but just imagine doing that. If we would apply the J minus to this, we would get some multiple, some wretched square root, times that target. Then when we apply J1 minus plus J2 minus to this side, we get 4 terms, because each of J1 minus and J2 minus works on this and this. So each of these two things generates 2 terms. When J1 minus works on this, we get J1 minus 2 times J2, J2 standing idly by. So let me just do this. We can say that J minus 2 is an amount of, and we could work out what this amount, it's straightforward to work out what this number A is going to be, but we won't do it, of J1 minus 2 times J2, J2. Then when J2 minus works on this, it produces some amount of J1 minus 1, J2, J2 minus 1. Right? Because it lowers this to J2 minus 1 whilst this stands idly by. Then when we use J1 minus on this, we get some more of what we've already got. This gets lowered to J1 minus 1, and we get some more of this, which we can absorb in this B. And then when J2 minus works on this, that goes down to a J2 minus. So we get plus another amount of J1, J2, J2 minus 2. Physically, what does this say? It says that if your box has its angular momentum tipped 2 units away from the z-axis, if you open the box, you may find 3 things. You will find one of 3 things. Either that the second gyro is still bang on the axis and the first is tipped 2 away, or that each of them is tipped a bit away from the axis, or that the first one is bang on axis and the second one is tipped 2 away. So it's perfectly reasonable. What you see when you open the box is what, in some sense, if you thought about it beforehand, you would have expected to see. This apparatus will deliver you the numerical values of A, B, and C, and therefore tell you the probabilities of those 3 outcomes. So we're getting complete information of what we will see if we do open the box. And we can plod on like this until we're completely worn out. The expressions will become, you can see, it looks as if these expressions as we go around here are getting more and more horrific, because if we apply if we do another lowering on this, apply J minus to this and J1 minus plus J2 minus to this, this will give us a term J1 minus 3, whilst and so on. So we'll have more terms. Mercifully, in the real world, when you're dealing with small values of J, there comes a point at which the lowering operator, J1 minus, will simply kill this because, for example, if J1 were the number 1, this would be J1 minus 1. And when the lowering operator worked on that, it would try and lower this to a number more negative than that, and it would kill it. So the expressions get more and more complicated as we go down here, and it turns out that when you go along here, they start to simplify because you get more and more of the lowering operators killing their targets. And you get sorted out, and you'll find that you arrive down here at j, comma, minus j. You will find that this is simply what it has to be physically, but you will discover that it is J1 minus J1 times J2 minus J2. That is to say, you will find automatically that when the box has its angular momentum in the minus direction, open the box, there's only one thing you can find, which is that both gyros are pointing in the minus z direction. And it's worth doing that, not in general j, but it's worth going all the way around, for example, for each of the j's are equal to 1, or one of the j's equal to 1, and one equal to a half, say. It's good to see that that happens. So in order now to complete the setup, there's one more thing we have to do, which is, well, strictly speaking, we should do some state counting, I suppose. Why don't we do some state counting? So the number of basis states. The number of basis states of the contents of the box is 2j1 plus 1 times 2j2 plus 1. This is the number of ways we're allowed to orient the angular momentum of the first gyro, and for each such orientation of the first gyro, this is the number of ways you can orient the second gyro. So that's the number of possible states of what's in the box. The number of states of the box should be the same because whether it's our choice to either think about the whole box or to think about what's in the box. So there should be as many states of the box as there are what's in the box. And how many have we got? So far, we've got 2 J1 plus J2 plus 1. Right? Because this is J1 plus J2, and going around this circle, we get 2 J1 plus J2 states. And that's much less than this if J1 and J2 are big. So we haven't got enough states. And it's intuitively evident that if you have two gyros in a box, their angular momenta don't have to be parallel to each other. They can be inclined. They might, for example, be anti-parallel, in which case you would have only, you think, J1 minus J2 of angular momentum. So what's the problem here is we've got all the states in which the two gyros are parallel to each other, despite what you might think by looking at these expressions here, right? Remember, these gyros have angular momentum other than what's appearing in the z direction. They've got angular momentum in the x and y directions as well. So this may look as if the two gyros are not parallel to each other, but they are. And there's a problem in problem set 5 about hydrogen, which illustrates that point. Okay, so these are all parallel to each other. So what we need is the states which are not parallel to each other. The way to go is to say, is to find what the expression is for the state, for this state, which is going to be the state J1, well, J minus 1, J minus 1. Because the two gyros are not parallel, there's a bit of cancellation of their angular momenta, but all the angular momentum of the box is parallel to the z-axis. That's this state here. This state is a linear combination. We've calculated it, in fact. It's a linear combination of this state and this state. And I argue on physical grounds that this state should be another linear combination, and it must be orthogonal to this because this is an eigenfunction, an eigenstate of the total j squared operator with an eigenvalue different from this. So I now argue that j minus 1, this is a state of the box, j minus 1, is a linear combination of j1, j1 minus 1 J2, J2, and J1, J1, J2, J2 minus 1. It must be a linear combination of these two. And we have to choose A and B so that it's orthogonal to the state we've already got. So comparing above, you can see by inspection the condition that J minus 1, J minus 1, J minus 1 equals naught, that equation implies that A is equal to minus the square root of J2 over J, and B is equal to the square root of J1 over J. If you put in these choices for A and B, you found a state which is orthogonal to that. And then you can, if you're a skeptic, you've got a well-defined state, you can apply J squared to it and show that it produces you the expected eigenvalue, and it's trivial to see that this thing has an eigenvalue J1 plus J2 minus 1 for the Jz. Having got this, we can apply the J minus operator mechanically to find this state and so on, all the way around down to here. And this is how we construct the states of the box. So we better talk a bit more about this. Time is up. We better talk a bit more about this on Wednesday, but we've got the main ideas.